Hi, dear MECH 205 students. This video record is about the resultant of a distributed load system, distributed force system. Uh, you know, free body diagram in say statics, dynamics, strength of materials is a very important diagram. Having a correctly drafted free body diagram can much more easily solve a problem. What is free body diagram? Well, everything is within the universe. Whenever we need to deal with a certain part of the universe, then yes, we focus our attention to that part. In the application, in practice, we isolate that part of the universe from its rest. The isolated part in the jargon is called the system, and the rest of the universe is called the surroundings of the system. And then what we have some effects applied by the elements of the surroundings onto the system. Between the system and the surroundings, yes, to be able to apply the forces onto the system, in practice we use some facilities, some tools. For instance, as an element of the surroundings, a person, a worker, may apply a force onto the system, onto the isolated part of the universe, by using a piece of rope. We connect piece of rope to the system at a certain point and then pull the rope. In statics, a rope, piece of rope, is considered as perfectly flexible element. So since it is perfectly flexible, using such an element, the member of the surroundings can apply only pulling type, tension type force onto the system. Similarly, if the facility to apply the force is a piece of chain, again we consider the chain as perfectly flexible facility. So while using a piece of chain, we can apply, surroundings can apply tension type force. When we use a flexible element to apply a force, tension force, of course, not pushing, we cannot apply pushing force, but can apply tension force. Whatever the inclination of the flexible element while the force being applied is, then the inclination of the line of action of the force through which it is applied onto the system will be the same. So if we know the inclination of the flexible element, this means we also know the inclination angle of the line of action of the force. It is applied by the surroundings to where? To the system. At this point, dear students, bring such a figure to the screen and then say that in the figure it looks like potato, a blue colored one, is our system. It has been isolated from the rest of the universe. Um, and the ones, one of them is the representative force as the element of member of the surroundings of this object, the earth, uh, applies uh, well forces, universal gravity law, in accordance with the universal gravity law. Well, each molecules of the material of the system will be attracted by the earth. Well, the resultant of such a force system is called the weight of the object, and its point of application is special, it is called center of gravity point. Here, this is the center of gravity point. It is commonly denoted using capital G, gravity point. And this one is the weight vector. Okay. If the contact area between the surface of the system and the surface of the tool that is used to apply the force onto the system is like this, relatively very small, then we assume that the area contact surface is as if a point, and say that the applied force is called point force or concentrated force. Okay, but if the contact area, well, there is a tool, okay, to apply the force, and the contact surface between the tool and the surface of the object is not very little, not to consider as if it were a point, but well, in a considerable size. In this example, for instance, here, well, we have a force system. It is applied by the surroundings, okay, thanks to the existence of a tool, and the surface of the tool, which is in contact with the surface of the object, is not negligible. Okay, if the force is applied not at that point, yeah, it is an idealization, but over a considerable surface to its area, then it is more common to express the load, not force, but force per unit of the contact area. It is, force per unit of contact area is the definition of pressure. Okay? Surface pressure, it is given surface pressure. Well, it is more common. Surface pressure, instead of knowing or giving the force, magnitude of the force, we express the pressure. Okay. In SI unit system, unit force per unit area in the honor of the scientist Pascal is expressed as Pascal, newtons per meter squared. Instead of saying newtons per meter squared, we say Pascal. Okay. But if the contact area between the surface of the tool, that is a facility to apply the force, and the surface of the system is slender like this, long but thin surface, and especially if the distribution, load distribution, pressure distribution, pressure is in one direction uniform, then well, it is more common. We multiply the size of the contact area, contact surface, let's say this distance B, okay, with the pressure B times the pressure, and then, well, we have the load not in Pascal unit, but we determine it, we obtain it, newtons per meter. Okay. Well, linear distribution, we say, if in one direction it is linear, say it is uniform, but the other direction it may be, well, in variation, then it is more common to express the load per unit of length. Well, we simplify the contact area as if it were a line, not a point, not a surface in considerable order, but as if it were a line. Okay, well, depending on the case, well, you know, if we have the system with the concentrated loads, these are applied by the surroundings onto the system, then, you know, we can find the resultant of such a system. How? Well, considering not only their translational effects, but also rotary effect. Well, find the resultant of the given forces. Considering their rotation effects. Well, relative to where? Relative to a certain, for instance, point A, reference point. You know, such a force system can be replaced with a equivalent force system. Say that in the end, at point A, we have a resultant force. It represents the net effect of the applied forces, F resultant, and a resultant couple moment. Resultant couple moment. Resultant couple moment represents the rotation effects of the forces, given forces, with respect to point A. Yes. Well, that system and this new system are equivalent. Well, to be able to find the equivalent system, well, for the same case, well, the requirement may be expressed differently. For instance, it may be said that, okay, find the resultant of the forces F1, F2, F3, and so on, with respect to point A. Or, in other words, it may be said, okay, find the equivalent system with respect to point A. Or, well, in other statement, it can be said, well, say that it is in practice not easy, even not possible to apply the forces at such points, okay, to set a certain effect onto the body, but we can easily do it while applying the force at point A. Not by appointing 1, 2, 3, 4, 5, n workers, or by using n different facilities and different ropes, chains, or piece of cables, whatever it is, the tool to use to apply the force, okay, onto the system. Just by using only one, how we can have the set the same effect. Okay, that is the another statement for the same result. It may be expressed like that. Well, all the cases, whatever the statement of the requirement is, the things to do are the same. Find the resultant of the given forces, of course, vectorly adding up. If the forces are coplanar, while using scalar expressions, we can find the resultant or the x component of the resultant and the y component of the resultant, and then find using Pythagorean theorem, find the resultant of the magnitude of the resultant. But in doing this, finding the resultant of the given force system, we must consider the rotational effects, some of the moments of the given forces relative to where. If the equivalent system is to be found determinate with respect to a certain point, at a point, well, say that instead of applying the forces onto the body, apply only one force at point A. Okay, if we know that the net effect of the given force system is to determine at point A, then yes, calculate the rotation effects of the forces, the moments of the forces with respect to point A. If we do this, then we obtain a resultant couple over there. Yes, well, if the force system is a distributed force system, distributed load, then yes, how can find the resultant of such a force system? Here's the question. Well, how can find the equivalent system to replace the given one? Well, if we have concentrated forces and also given couple vectors, well, in previous chapters sufficiently studied on such things, and in the end we have a resultant force, okay, to apply at point A. Why at point A? Because point A is quite suitable to apply a force. The other points are not suitable. We have some obstacles and say that in practice impossible to apply a chain or piece of cable or say apply the force using a rod. It is practically either not easy or impossible. But point A is quite suitable to apply the force. Okay, find the resultant of the given force system, and not by applying n force, but only by applying one force at point A, and also when applying a resultant couple onto the body, we can set the same effect onto the system. You know this. Okay. Yes. Now change the slide. Let me. Okay. Yeah, yes. Well, here in the example, well, we have a beam. Okay, where is the beam? Oh, sorry. Well, first clean. Yeah, beam is over there. Well, over the surface, top surface of the beam, there is a load. But load is, you see, over the surface, not at a certain point. It has been distributed load. Well, the question is the same. How we can find the resultant of such a force system, such a load, or in other words, say that how we can replace this load system, force system, with an equivalent one. For instance, equivalent system is to be the one the resultant force is to apply at this point, let's say point O, okay, and applying the force, it is the representative force, it is the resultant of the distributed load, okay, at point O. But in doing this, we need to consider the rotation effects of the components of the given distributed load system. You know, where if the forces are not passing through the same point, not concurrent, then, well, they can set not only translation effect onto the bodies, but also rotation effects. In finding the equivalent system or in finding the resultant of the given force systems, we must consider the translation effects and also rotation effects. How? Well, add the forces up, find the resultant, calculate the rotation effects moments with respect to a reference, okay, and then add the moments up. Well, the thing to consider at the intermediate stage, we consider the force not applied at the given point, but at a more suitable point. But in doing this, we have a force. It had to be applied, for instance, at point A, but it is not possible to apply the point, say, force at point A because of some restrictions, obstacles, etc. But the force can be applied at point, let's say, O. To be able to have set the same effect, that would be set applying the force at point A. Well, when we apply the force not at point A but say point O, yeah, yes, to be able to set the same effect, we must consider the rotation effect of this force. Instead of applying force at point A, if we apply it at point O, like this, then we must consider its rotation effects. In doing this, to be able to have the given system equivalent with the new one, the thing to do is that at the intermediate stage, while we are applying force not at point A, but point O, and it is negative as well. Well, this plus that is 0, so well, this new system is equivalent with the first one. Well, here, distinguish, well, this force and that force are parallel to each other. Well, magnitudes are the same, but the sense opposite. This and that form a couple. Okay, couple. Yes, well, couple is a free vector, but since we consider the force not applied not at point A but point O, now couple, magnitude of the couple must be calculated when for this force relative to point O. Okay, and relative to point O, find the couple because well the distance between the couple forces of the couple, you know, extends from point O to the line of action of this force. Okay, well, calculate the moment of the couple accordingly. In practice, just calculate the moment of this force with respect to point O. You know this. Yeah, yes, here, to be able to find the resultant of such a distributed load, the thing to do is the same. Find the resultant of the forces, and also find the resultant of the moments. Okay. Well, as I said already, if the contact area, yes, see the contact area, it is not negligible. It is, well, in this example, over the entire of the top surface of the beam. Well, since the contact area is not negligible, so well, we express the load using pressure definition. Yeah, yes, P is more common. Unit is Pascal, and the load is called distributed load. How we can find it as resultant? Well, here this is a special case. In this example, the case is special. Well, you know, along the x-axis in the x direction, the pressure is not uniform. Pressure changing. Here it is greater, there it is smaller. There is a distribution. In the x direction, it is not uniform. But in the special case, in the other direction, let's say y direction, it is uniform. It is uniform. If the distributed load is in such a characteristics, then well, it is the common practice. It is quite common. Well, we multiply the distributed load. It is expressed as pressure, surface pressure, by the dimension of the contact surface. It is the dimension. It is parallel to the axis. When along that axis, the load is uniform. Multiplying P by the dimension of the surface, okay, it is parallel to the y-axis in this example, and well, in that direction load is uniform. We obtain the distributed load, well, not in pressure unit, but force per unit of distance per line. Well, not pressure, but after multiplying the surface pressure by such a dimension, well, it is expressed as, well, let's say W. It is not to say weight, lowercase v, W. It is unit going to be not force per meter squared, newtons per meter squared, but newtons per meter. Well, the load curve will be not in pressure unit. Load won't be in pressure unit, but well, force per unit of length. Okay. Well, If it is the case, well, how can find the resultant of the distributed load? Well, over the surface, contact surface, take a smaller part. Well, its area, contact area, is equal to delta A. Okay, and then, well, this is the curve, load curve, and a unit is not distance, be careful, unit is pressure. We have diagram, load diagram. Well, load diagram is, well, over here. In the example, it is the function of x. Pressure distributed load is expressed in unit of pressure, and pressure is a function of x, not function of y. Okay. So, well, consider such a prism. It extends from the contact surface to the load curve, pressure curve, pressure diagram. It is almost rectangular prism. Okay, the volume of the prism, delta V, let's say, volume, volume is defined for a rectangular prism, approximately is equal to, well, delta X, area, delta A, contact area, times the height of the prism. But this prism is special. Well, in this direction, unit is not distance, it is pressure. Okay, because, well, the rectangular prism extends from the surface, contact surface, to the load diagram. So the height of the prism is P. Well, here in this region, it is equal to that much. Well, it is what? It is the volume. Well, this part of the load is equal to the volume of this rectangular prism. If you take the area, contact area, as infinitesimally small, then the corresponding volume, it is under the load diagram, will be infinitesimally small. Okay, P times dA. P times dA. Okay. Well, this is the this part, P times dA. Actually, well, this term is the magnitude of the load. It is being applied onto that part of the contact surface. Okay, this is actually the force applied onto that part of the contact surface, onto the object at its contact surface. But this term also, you see, is the volume under the load curve. So to be able to find the resultant, okay, of the given distributed load system, the thing to do is that take the integral from this point to that point, where from 0, origin is over there, let's say, to this point. These are the limits of the integral. The result is the resultant force, F, resultant of this distributed load system. But it is also equal to the volume under the load curve. Volume under the load curve. Yeah, yes. If we know the as the load, the pressure value, surface pressure, just by finding the volume of the space under the load diagram, then can consider the result as the magnitude of the resultant of the distributed load. Okay. But of course, since the load, the forces are not concurrent, in adding the forces up to find the resultant, we must also consider their rotation effects. Rotation effects. Yes. Okay. Find if the selected reference point is this point, okay, point O, then for each elements of the forces, for each force, find the moment of it with respect to this reference point. Okay. Well, for instance, when under the load diagram, we selected such a part, contact area is infinitesimally small. Okay, well, this is our beam. Okay, this is point O. Well, over the surface of the beam, we selected infinitesimally small contact area, dA, and well, we have the load diagram, where the prism extends from the surface of the object to the load diagram. Okay, and where we have what the corresponding force, load. If we multiply the contact area over here with the pressure at that place, then it is going to be the magnitude of the force. Okay, due to the existence of the load, distributed load, that part of the system will be under the action of such a force. Since the contact area is infinitesimally small, the magnitude of the force, now let me indicate that force using red color, where this force is infinitesimally small. Okay, then it is one of the forces applied onto the surface of our system. It is a beam due to the existence of distributed load. But since the reference point is O, we must calculate the rotation effect of this force with respect to this point. You know the thing to visualize at or consider at the intermediate stage, to be able to have the force not here but applied as if at point O. The thing to visualize is that we have dF here, and also it is negative, minus dF. Yes, minus dF and dF form a couple. So well, this means to be able to have the effect of find the effect of this force at point O. In other words, to be able to find the equivalent for this force, okay, at point O, the thing to do is that, well, calculate the moment of this force with respect to the reference point. It is going to be the magnitude of this couple. Okay, then calculated moment of df, this force, with respect to point O. How much? Distance is from here to there is, let's say, x millimeters, x times df. Okay. Well, this is the moment of one of the forces, but well, under the load curve, we have infinite number of prisms. Okay? In other words, infinite number of tiny differential forces. Adding the forces up, we obtain the resultant force. Well, you know, df, actually, x times df, from here we concluded that is the volume under the load diagram. Well, how much it is? The pressure at the place where we considered that part of the contact surface, its size is infinitesimally small, times the contact area. Well, P times D is the magnitude of this differential force. Times the moment length, the distance between this and that, relative to point O, is the moment. Okay, well, this is the moment of this force. How many forces we have? Infinite number of forces. For each, calculate the moment and then add them up. Since the forces are parallel to each other, well, you know, easily can add them up, well, using integration. If we take the integral on the both sides, we find the resultant couple moment with respect to O, and it is equal to x times, where PdA is the volume under the load curve, x times the volume. This volume is the volume under the curve, the volume of the space under the curve. Okay, well, that is the resultant moment. So, well, at the intermediate stage, well, for the given distributed load system, that is going to be equivalent. That is the beam. Okay, well, here at point O, we have the resultant force, and at point O, we have resultant couple, and couple, resultant couple, with respect to point O. Well, it represents the rotation effects of the forces. Okay, these are applied due to the existence of such a distributed load. Well, the couple vector, resultant couple vector, is perpendicularly oriented with respect to the resultant force. You know, whenever the line of action of resultant force and the line of action of the resultant couple is perpendicular with respect to each other, then when that system, such a system, resultant couple, resultant force system, can furtherly be reduced to what? To a single resultant force. Well, this system is equivalent to that one. Where if we slightly force, resultant force, or consider apply the resultant force not at point O, but say at point, let's say N, then, well, this force, resultant force, can represent not the translational effect of the given distributed load, but also their rotational effect with respect to point O. Okay, well, the distance from the reference point to the line of action of this resultant force in this figure has been indicated with this symbol, x bar. Okay, x bar is the location dimension relative to the reference point. Okay, but at such a distance away, if we apply the resultant force, then it is effect going to be the same that of the given distributed load. Okay, well, actually, if we consider that this integration is what is the resultant of the rotation effects of the distributed load with respect to point O, but since, well, we have the load curve, and well, this term is the volume under the load curve, well, and also the magnitude of the resulting force is equal to what? Well, P times dA, integral of this one, but it is, for the given load curve, it is the resultant force is equal to the volume under the load curve. Then, well, here in finding value x, well, value x, let me use this part to write an expression. Well, x is equal to x bar is equal to volume under the load curve, total volume under the load curve, here total volume under the load curve, well, is equal to the magnitude of the resultant force. Okay, integral of x e volume. Actually, this expression gives us the coordinate of the centroid of the volume, center of the volume. Yeah, yes. This is the same formula that is used for finding the centroid of a volume. But from this analysis, from such an interpretation, can conclude that, well, the coordinate, okay, of the line of action of the resultant force with respect to reference point, well, it represents, that force represents the total effect of the distributed load with respect to point O. That location dimension is equal to the coordinate of the center of the volume. Which volume? Volume under the load curve. Okay. So, well, in practice, in finding the resultant of a distributed load, the thing to do is that find the volume under the load curve, and the result is the magnitude of the load, resultant force. If we know or can find the centroid of the volume under the load curve, then its coordinate will also be the coordinate for the resultant force Okay, such a distance away, the resultant force is to apply to be able to set the same effect that of the distributed load. Okay, yeah, yes. Well, if the distributed load is uniform in one direction but not uniform in the other direction, then when multiplying the given load, it is denoted, expressed, given as pressure, surface pressure, by the dimension of the contact surface. Okay, it is the dimension in the sense of an axis, while in this direction the distribution is uniform. Then, well, can have load curve not in the unit of pressure but in newtons per meter in SI unit system. Okay, yes. In such a case, yeah, yes, the load curve, load is given uh, per unit length, P times the dimension of the contact surface in the direction the pressure is uniform, then we have the load curve in this unit, newtons per meter. Yeah, the most common type of distributed loading encountered in engineering practice can be represented along a single axis. For example, consider the beam or plate in figure A. Here is figure A. Okay, that has a constant width and is subjected to a pressure loading that varies only along the x-axis. This load can be described by the function pressure distribution. It contains only one variable x. It depends on the x value only. In the x direction, it is a distribution, not uniform, but in the other direction, it is uniform. Okay, so if the load is a coplanar distributed load, well, the load is given not in the unit of pressure, but a unit of newtons per meter. Okay, we multiply the load function, uh, surface pressure, by the width of the contact surface. Okay, in that direction, load is uniform. So we obtain another load expression, not in pressure unit, but newtons per meter. Okay. And then making a similar interpretation, well, to be able to find the resultant of such a force system, distributed load, well, select infinitesimal contact, infinitesimal small portion over the contact surface. Okay, it is value